Here's a problem that uses forces to find speeds and distances and things. What you have is a wire that's the textbook calls a slide wire, a wire that slides along this U-shaped metal rail. The wire has length L, mass M, resistance R, which I forgot to write here, but there is a resistance R, and a uniform magnetic field pointing into the plane. So everywhere in this picture is a magnetic field pointing into the plane. The wire is pushed or something so that it has an initial speed V0 to the right. There's no friction between the slide wire and this loop, and the resistance of the loop is negligible, so the only resistance, electrical resistance, is in the slide wire. And so the issues are to find an expression for the force F on this slide wire while it's moving a speed V. Find the distance that the slide wire moves before coming to rest. So if it's moving to the right at speed V and eventually comes to rest, it's a pretty good guess right now that the force is going to be to the left. But let's think about this. What's going on here? Well, you have a conductor that's moving to the right. It's got a velocity to the right. So the electrons in that conductor, the mobile electrons, the conduction electrons, have a force on them. You can tell the direction of the force by the right-hand rule. The right-hand rule will tell you that the electrons, because they're negatively charged, are being pushed down this slide wire, from the top of the slide wire down to the bottom. That's the direction that they're being pushed. You can conclude a couple of things from that. One, that the slide wire ends up with a lower electric potential at the bottom of the wire. So down here is going to be a smaller electric potential. Because electrons are being pushed this way, this will end up being slightly negatively charged. This will end up being slightly positively charged. This will be the higher electric potential. That will be the lower electric potential down here at the bottom. Because of that difference in electric potential, a current will flow. Counterclockwise current. So that's the other thing you can conclude. A counterclockwise current will flow around this thing. Of course, you could have concluded the same thing by thinking about Faraday's law, thinking about the change in magnetic flux through this loop right here, and you would have gotten the same result. You would have found that the EMF induced in this loop is the time rate of change. Down here I've written this out. The EMF induced in the loop is the derivative with respect to time, in other words, the time rate of change of the flux, the magnetic flux B times the area. The area is the length L times velocity times time will give you this distance. So the derivative of that, there's a single t, so the derivative of that is just the EMF is the magnetic field times the speed times the length. And that EMF is equal to IR, so you can solve for the current that goes counterclockwise around this loop. Now, a current that goes up this wire in a magnetic field is going to have a force on, is going to give you a force on the wire. Current goes up the wire, magnetic field points into the board. You know, the same right-hand rule, but now for this current moving this way, we'll show you that there's a force to the left, a magnetic force to the left on this slide wire. Just what the problem suggested. A magnetic force to the left will give you an acceleration to the left, meaning the velocity is going to be getting smaller as time goes on. Again, the calculation, the slide wire has length L, has a current I in it. It's in a magnetic field B. B and I are perpendicular to each other, so the force is just I times L times B. I we already know, so we can plug that in, and then we have an expression for the force. Now find the distance the wire moves before coming to rest. Well, there's a funny thing about this force that we have. It depends on the velocity. So the force is pushing to the left. As it pushes to the left, the velocity will go down. And you can see as the velocity goes down, as the speed goes down, the force goes down. So as this thing moves to the right, it will be going slower and slower and the acceleration will be getting smaller and smaller because the force is getting smaller and smaller. You can probably guess at this point, maybe guess at this point, that what's going to happen is that the velocity is going to exponentially go down towards zero. But we can see this for more carefully, but it's just by using Newton's second law. dv dt is the acceleration, and that's the force per unit mass. So dv dt, we can plug in the force, and we get this equation for dv dt. Negative sign because the acceleration is decreasing the speed. We can rearrange this to get all the speed parts on the left. Divide this v over here. dv over v is minus this quantity times dt. Integrate both sides from v0, which is where it started, to any time, any later time. So any later velocity v of t. Integrate both sides, 0, t equals 0 to some later time. What we find is the log of vt over v0 is this quantity multiplied by t. It's linear in t, which tells us that v is indeed exponentially decreasing. T equals 0 is v0, and for long enough t, in other words, infinite t, it stops. Now, how far did it go? Well, just keep going. We know that v of t is dx dt, so we can write that as dx is v of t dt. Again, after we plug in v of t that we've already found, integrate both sides, find x of t is equal to this expression, and set t equal to infinity, because that's how long it takes to stop, and you find out that this is where x is. This is how far it's gone in that time.